Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the silent, ancient world of glaciers. These vast rivers of ice have shaped our planet for millions of years, carving valleys, sculpting mountains, and holding within them the frozen memories of Earth's climate. They are both powerful and delicate, moving with patient determination across landscapes that seem eternal. Glaciers are witnesses to time itself, recording centuries in layers of compressed snow and ice. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of these frozen giants to carry you into peaceful sleep. Let's begin. The nature of ice glaciers are rivers of ice that flow like frozen honey across the land. When you think of a river, you imagine water rushing and tumbling over, rocks, moving with visible speed. But glaciers are different. They flow too, but so slowly that the movement is invisible to watching eyes. Made of compressed snow that has accumulated over decades or centuries, glaciers transform from fluffy powder into dense, crystalline ice. Under their own tremendous weight, they begin to move, flowing downhill like cold molasses. Some glaciers advance only a few centimeters per day. Others surge forward at meters per hour during rare events. The ice within them deforms and shifts, carrying rocks, soil, and ancient air bubbles trapped from atmospheres long past. To stand beside a glacier is to witness geology in motion, a river frozen in time yet paradoxically alive with movement. Ice in a glacier can be hundreds of thousands of years old. Deep within the heart of ancient ice sheets lies frozen time. The snow that falls today will eventually be compressed into ice, buried under layer upon layer of subsequent snowfall. As centuries pass, this ice sinks deeper, pressed down by the weight of everything above it. In places like Antarctica and Greenland, scientists have drilled cores thousands of meters deep, retrieving ice that fell as snow during the last ice age. Some of this ice is over 800,000 years old, containing tiny bubbles of ancient atmosphere, microscopic particles of dust from distant volcanic eruptions, and chemical signatures of climates long vanished. To study glacier ice is to read Earth's diary, written in frozen water. Each layer tells a story of temperature, precipitation, and atmospheric composition. The ice remembers everything, preserving it in crystal clarity for millennia. Glaciers hold nearly 70% of Earth's fresh water. If you were to gather all the fresh water on Earth's surface, nearly 3/4 of it would be locked in ice. Glaciers and ice sheets contain vast reserves, dwarfing all the lakes, rivers, and swamps combined. The Antarctic ice sheet alone holds enough water to raise global sea levels by nearly 60 meters if it were to melt completely. Greenland's ice sheet could add another 7 meters. These frozen reservoirs represent not just water, but potential. They influence ocean currents, regulate climate, and sustain ecosystems that depend on glacier-fed rivers. Indigenous communities in the Andes, the Himalayas, and other mountain ranges have relied on glacier meltwater for agriculture and drinking water for thousands of years. To understand glaciers is to understand one of Earth's most vital resources, held in suspended animation, waiting in the cold stillness of perpetual winter. The blue color of glacier ice comes from compressed density. When you see a glacier up close, the most striking feature is often its color. While snow is white, reflecting all wavelengths of light equally, old glacier ice glows with an ethereal blue. This happens because the ice is so dense that it absorbs the longer wavelengths of light, the reds and yellows and oranges, while allowing the shorter blue wavelengths to pass through and scatter back to your eyes. The deeper and older the ice, the more intense the blue becomes. Crevasses and ice caves reveal this color most vividly, with walls that seem to glow with their own inner light. It is the blue of deep ocean water, of twilight skies, of sapphires. Ancient peoples who encountered these blue depths must have thought them magical, and in a way, they were right. The color is a physical manifestation of time and pressure, beauty created by the patient work of centuries. Some glaciers contain layers of ancient volcanic ash. Within the frozen layers of glacial ice lie dark streaks and bands, evidence of violent events from Earth's past. When volcanoes erupt, they send plumes of ash high into the atmosphere, where winds carry the particles across continents and oceans. Eventually, this ash falls to the ground, settling on snow-covered glaciers. Over time, it becomes buried and compressed, along with the snow, forming distinct layers within the ice. Scientists use these ash layers as time markers, matching them to known eruptions and creating chronologies that span thousands of years. Some layers come from eruptions that occurred on distant continents, carried around the globe by atmospheric currents. Others mark catastrophic explosions that changed climate patterns for years afterward. These dark bands are more than geological curiosities. They are records of Earth's restlessness, moments when the planet's interior burst forth, leaving signatures that glaciers faithfully preserve. Glaciers can hold trapped air bubbles from ancient atmospheres. One of the most remarkable features of glacier ice is its ability to capture and preserve tiny samples of the atmosphere from when the snow first fell. As snow accumulates and compresses into ice, small pockets of air become sealed within, creating microscopic time capsules. When scientists drill ice cores and extract these bubbles, they can analyze the ancient air directly, measuring concentrations of carbon dioxide, methane, oxygen, and other gases. This has allowed researchers to reconstruct Earth's atmospheric history with astonishing precision, revealing how greenhouse gas levels have fluctuated naturally over hundreds of thousands of years. The bubbles show us that our current atmospheric composition is unprecedented in recent geological history. They also provide evidence of how temperature and atmospheric gases are intimately connected. Each bubble is a frozen breath from the past, a whisper from climates we can only imagine, preserved perfectly in the patient embrace of ice. Glacier formation glaciers begin as accumulated snowfall in regions where winter snow survives the summer. Not all snow becomes a glacier. For ice to accumulate and persist, the climate must be cold enough that winter snowfall exceeds summer melting. This happens in polar regions and at high elevations in mountains around the world. Year after year, snow piles up, each winter's layer adding to those beneath. Over time, the weight of new snow compresses the older layers below, squeezing out air and transforming the crystalline structure. What begins as light, fluffy snow gradually becomes firm, a granular intermediate stage, and eventually dense glacial ice. This process can take decades or centuries, depending on temperature and accumulation rates. The requirement is simple but specific: cold, consistent, patient. Only where these conditions persist can glaciers be born, making them indicators of climate, markers of places where winter never fully releases its grip. The transformation from snow to glacier ice takes many years. The journey from snowflake to glacier ice is long and gradual. Fresh snow is mostly air, light enough to drift on the wind. As it accumulates, the weight of each new layer compresses those below. Air pockets shrink. Crystals bond together. After a year or more, the snow becomes firm, denser than fresh. Snow, but not yet true ice. The transformation continues. More layers accumulate. More compression occurs. Eventually, when the density reaches about 830 kilograms per cubic meter, the material has become glacial ice, solid and impermeable. This entire process typically takes between 10 and 100 years, depending on temperature and snowfall rates. In Antarctica, where cold is extreme and snowfall sparse, it may take centuries. In warmer mountain glaciers with heavy precipitation, the transformation happens more quickly. Either way, patience is required. Glaciers do not rush. They are built slowly, one winter at a time. Glaciers require a balance between accumulation and melting to survive. Every glacier exists in a delicate equilibrium between growth and loss. At higher elevations, in the accumulation zone, snow falls and compresses into ice faster than it melts. Lower down, in the ablation zone, melting and sublimation remove more ice than is added. The boundary between these zones is called the equilibrium line, and its position determines whether a glacier advances or retreats. When accumulation exceeds ablation, glaciers grow and push forward. When melting dominates, they shrink and withdraw. This balance is sensitive to temperature and precipitation. A few degrees of warming can shift the equilibrium dramatically, exposing lower reaches to melting while reducing snowfall at higher elevations. Glaciers are in constant negotiation with climate, responding to changes that may seem subtle but have profound effects. They teach us that stability is not static but dynamic, a continuous adjustment to surrounding conditions. Some glaciers can be thousands of meters thick. The depth of glacial ice is difficult to comprehend until you stand before it or consider the numbers. The Greenland ice sheet, in places, reaches thicknesses of over 3,000 meters. That is nearly 2 miles of ice. Layer upon layer of compressed snow accumulated over hundreds of thousands of years. The Antarctic ice sheet is even thicker in some locations, exceeding 4,000 meters. The sheer mass of this ice is staggering, weighing so much that it depresses the Earth's crust beneath it, pushing continents downward into the mantle. If you could drill through from top to bottom, you would pass through centuries of climate history, encountering ice from the medieval period, the Roman Empire, the Stone Age, and far beyond. The deepest ice contains snow that fell when Neanderthals still walked the Earth. To imagine such depth is to grasp the patience of geological processes, the slow accumulation that builds mountains of ice grain by grain. The weight of glaciers can depress the land beneath them. Ice is heavy. When thousands of meters of it accumulate over centuries, the weight becomes immense, literally pushing down on the Earth's crust. This is called isostatic depression, and it is measurable and significant. In Greenland and Antarctica, the bedrock has been pressed down by the ice sheets, in some places sinking hundreds of meters below sea level. When glaciers retreat and the ice mass is removed, the land begins to rebound, slowly rising back up like a cushion recovering its shape. This process, called isostatic rebound, is still happening today in places that were covered by ice sheets during the last glacial period. Scandinavia, Canada, and parts of the northern United States continue to rise slowly as the Earth's crust adjusts to the absence of ice that melted 10,000 years ago. The land remembers. Even after the ice is gone, its influence persists, shaping coastlines and altering landscapes for millennia. Types of glaciers vary. Glaciers flow down mountain slopes like frozen rivers. In mountainous regions around the world, glaciers form in high basins and flow downward through valleys. following the path of least resistance, much like water would. These valley glaciers, also called alpine glaciers, are among the most accessible and visually striking. They wind between peaks, their surfaces marked by crevasses and medial moraines where tributary glaciers merge. The Alps, the Rockies, the Andes, the Himalayas all host valley glaciers, some stretching for tens of kilometers. As they descend, they carve and shape the valleys through which they move, deepening them into characteristic U-shapes. At their lower ends, they may terminate in meltwater rivers or carve into lakes. These glaciers have inspired explorers, artists, and scientists for centuries. To hike beside one is to walk alongside a living force of nature, powerful yet slow, ancient yet constantly renewing itself through the cycle of snow and ice. Ice sheets are vast expanses covering entire continents. While valley glaciers are impressive, they are dwarfed by ice sheets, massive continental glaciers that cover millions of square kilometers. Only two major ice sheets exist today: Antarctica and Greenland. These are not glaciers in valleys, but continuous expanses of ice that bury entire landscapes beneath kilometers of frozen water. Antarctica's ice sheet is by far the largest, containing about 26.5 million cubic kilometers of ice. If you could stand at its center, you would see nothing but white in every direction, a frozen desert extending to every horizon. The ice moves outward from the center under its own weight, flowing toward the coasts where it either carves into icebergs or forms vast floating ice shelves. Ice sheets are remnants of ice ages, periods when ice covered much more of Earth's surface. They represent the planet's deep freeze, holding within them enough water to reshape coastlines if released. Ice shelves float on the ocean while still attached to land. Where ice sheets meet the sea, they do not always stop at the shoreline. Instead, they may extend outward as floating platforms called ice shelves. These massive structures can be hundreds of meters thick and cover areas larger than many countries. The Ross Ice Shelf in Antarctica is roughly the size of France. Ice shelves are fed by glaciers flowing from the interior, and they remain attached to the land even as they float on seawater. This creates a unique dynamic. They are part of the ice sheet, but also interact with the ocean. Ice shelves are important because they act like buttresses, slowing the flow of glaciers behind them. When ice shelves collapse, as several have in recent decades, the glaciers they once restrained can accelerate, flowing faster toward the sea and contributing more to sea level rise. They exist in a precarious balance between ice and ocean. Tidewater glaciers meet the sea and carve icebergs directly into the ocean. Some glaciers do not end on land, but flow all the way to the sea, their massive fronts towering above the water. These are tidewater glaciers, and they are dramatic both in appearance and behavior. At their termini, huge chunks of ice break off and crash into the ocean in a process called carving. The sound is like thunder, echoing across fjords and inlets. Each iceberg that carves represents ice that accumulated far inland, traveled slowly down the glacier, and finally broke free to drift in the sea. Tidewater glaciers are found in Alaska, Patagonia, Greenland, and Antarctica. They create some of the most stunning landscapes on Earth, with blue-white ice walls rising from dark waters, surrounded by mountains. These glaciers are also sensitive to warming, as warmer ocean water can melt the ice from below, destabilizing the glacier front and accelerating carving. They are beautiful, but also indicators of change. Piedmont glaciers spread out like fans at the base of mountains. When valley glaciers emerge from confined mountain valleys onto flat plains, they sometimes spread outward in broad, fan-shaped lobes. These are Piedmont glaciers, and they form where ice is no longer constrained by valley walls. The Malaspina Glacier in Alaska is a classic example, a massive lobe of ice covering over 3,900 square kilometers. From above, it looks like frozen drapery, flowing outward in ripples and folds. Piedmont glaciers demonstrate the plastic nature of ice, how it can deform and spread under its own weight when given space. They are less common than valley or ice sheet glaciers, requiring specific topographic conditions. But where they exist, they are spectacular, blending the features of mountain glaciers with the expansive scale of ice sheets. They are transitional forms, caught between the confinement of mountains and the freedom of open landscapes. Hanging glaciers cling to steep mountain slopes. Not all glaciers rest on flat surfaces or flow down gentle slopes. Some cling precariously to steep mountainsides, seemingly defying gravity. These hanging glaciers are small and steep, perched on high cliffs and rock faces. They are fed by snow avalanches and accumulation in high basins, and they are unstable by nature. Occasionally, portions of hanging glaciers break off, triggering ice avalanches that roar down mountainsides. Climbers and mountaineers approach them with respect and caution. Despite their small size compared to valley glaciers or ice sheets, hanging glaciers play important roles in local ecosystems, feeding streams during dry seasons and influencing mountain weather. They are reminders that ice can exist in extreme environments, finding purchase even on nearly vertical terrain. Their presence marks the boundary where cold is just sufficient, where the battle between gravity and ice reaches a delicate truce. Cirque glaciers nestle in mountain hollows like frozen pools. High in the mountains, where peaks scrape the sky, small glaciers form in bowl-shaped depressions called cirques. These cirque glaciers are often the birthplaces of larger valley glaciers, accumulating snow and ice in protected hollows carved by previous glaciation. They are intimate in scale, small enough to take in with a single glance, yet they possess all the essential features of their larger cousins. Cirque glaciers erode the rock beneath and around them, gradually deepening and widening their basins. When they melt away, they leave behind cirque lakes, jewel-like tarns that sparkle in the sun. Hikers seeking alpine solitude often encounter these glaciers, their surfaces smooth or broken, depending on the slope. They are the smallest and highest glaciers in many mountain ranges, existing at the very limit of where ice can persist. They mark the frontier of the frozen world. How glaciers move. Glaciers flow under their own weight like thick fluids. Ice seems rigid and solid, but under enough pressure, it behaves like a very thick fluid. This is the key to understanding how glaciers move. The immense weight of accumulated ice creates pressure at depth, causing the ice crystals to deform. Individual crystals slide past one another. Layers shift. The ice flows, not like water, but slowly, ponderously, like cold honey. This internal deformation is called plastic flow, and it allows glaciers to move even on gentle slopes. The rate depends on thickness, temperature, and steepness. Warmer ice deforms more easily than colder ice. Thicker glaciers exert more pressure and flow faster. The movement is measured in centimeters per day for some glaciers, meters per day for others. To watch a glacier over weeks or months is to see this flow in action, a frozen river making its way downhill with patient inevitability. Basal sliding occurs when meltwater lubricates the glacier's base. Not all glacier movement comes from internal deformation. Another mechanism is at work, sliding along the bed. When pressure and friction at the base of a glacier generate heat, or when surface meltwater percolates down through cracks, the ice at the bottom can reach its melting point. This creates a thin layer of water between the ice and the bedrock. Lubricated by this water, the entire glacier can slide forward more quickly. This is called basal sliding, and it can dramatically increase glacier velocity. In summer, when more meltwater reaches the base, glaciers often speed up. In winter, when freezing conditions dominate, they slow down. The interaction between ice and water at the glacier bed is complex and crucial. It affects not just how fast glaciers move, but also how they erode the landscape beneath them, carving valleys and smoothing rock surfaces. Crevasses form where ice is stretched and cracked. As glaciers flow, they do not move uniformly. Faster flow in some areas and slower flow in others creates tension within the ice. Where the ice is stretched, it cracks, forming deep fissures called crevasses. These can be narrow slots or gaping chasms, sometimes over 30 meters deep. Crevasses form in zones where the glacier passes over bedrock steps, curves around corners, or accelerates down steep slopes. They are dangerous for travelers, hidden by snow bridges that can collapse without warning. Yet they also reveal the internal structure of the glacier, exposing layers of ice accumulated over years. Crevasses are beautiful in their geometry, clean lines cutting through white and blue ice. They are evidence of stress, the glacier's response to the landscape it must navigate. Over time, as the ice moves, crevasses close and new ones open, a constantly changing pattern written across the glacier's surface. Some glaciers surge forward suddenly after long periods of slow movement. Most glaciers move at steady, predictable rates, but some behave differently. These surging glaciers remain relatively stationary for years or decades, then suddenly lurch forward at speeds many times their normal rate. A surge might last months or years, during which the glacier advances kilometers, sometimes overriding forests or blocking rivers. The causes of surging are complex, involving interactions between basal water pressure, ice thickness, and bed conditions. When pressure builds up and the glacier's base becomes saturated with meltwater, the ice can decouple from the bedrock and slide rapidly. After the surge, the glacier returns to quiescence, accumulating mass until conditions trigger the next event. Surging glaciers are found in Alaska, Iceland, the Himalayas, and other regions. They remind us that glaciers are not always gradual. Sometimes, even ice can be explosive, dramatic, and unpredictable. Glaciers move faster in their centers than at their edges. Like rivers, glaciers do not flow uniformly across their width. Friction with the valley walls slows the ice at the edges, while the center, unimpeded, moves faster. This differential movement creates patterns on the glacier surface. Rocks and debris deposited in straight lines across a glacier's width will, over time, curve downstream, fastest in the middle, slowest at the sides. This is why medial moraines, the dark stripes running down glaciers, often curve gracefully. The same principle applies vertically. Ice at the surface, under less pressure, moves faster than ice deep within the glacier, which is held back by friction with the bed. Understanding this velocity gradient is important for scientists modeling glacier behavior and predicting how glaciers will respond to climate change. It also adds to the beauty of glaciers, whose surfaces are shaped by the invisible currents of ice flowing beneath. Ice can flow uphill under the right conditions. It sounds paradoxical, but under certain circumstances, glacier ice can flow upward. This happens when the ice behind exerts so much pressure that it forces the ice ahead to move in any available direction, even against gravity. In valleys with uneven beds, ice can be pushed up and over bedrock bumps. In ice sheets, the flow is outward in all directions from the high center, meaning ice flows upslope on the far sides of domes. This is not ice-defying physics, but responding to pressure gradients. The ice is so thick and heavy that the pressure at depth overwhelms local topography. It is a reminder that glaciers operate on scales where intuition can mislead. What seems impossible at human scales becomes routine when thousands of meters of ice are involved. Ice flows where pressure dictates, and gravity is only one of several forces at play. Glacier landscapes. Glaciers carve U-shaped valleys as they move. One of the most distinctive legacies of glaciers is the shape of the valleys they leave behind. Unlike rivers, which carve narrow, V-shaped valleys, glaciers create broad, U-shaped troughs. This happens because glaciers erode not just the bottom of the valley but also the sides, plucking rock from walls and smoothing surfaces as they flow. The result is a valley with a flat or gently sloping floor and steep, straight walls. After the glacier retreats, these valleys remain, often filled with rivers that seem too small for their surroundings. The U-shape is so characteristic that geologists can identify past glaciation by valley morphology alone. Famous examples include Yosemite Valley in California, Lauterbrunnen Valley in Switzerland, and countless fjords in Norway. These valleys are testaments to the erosive power of ice, landscapes transformed by the slow, grinding passage of frozen rivers. Fjords are drowned glacial valleys filled with seawater. When glaciers carve valleys that extend below sea level and the ice later retreats, the ocean can flood in, creating fjords. These are among Earth's most dramatic landscapes, steep-walled, deep, narrow inlets that reach far inland, with mountains rising directly from dark water. Fjords are common in Norway, Greenland, Alaska, Chile, and New Zealand, places where glaciers once reached the sea. The depth of fjords can be staggering, sometimes over 1,000 meters, deeper than the surrounding ocean floor. This depth reflects the erosive power of thick glacial ice, which carved the valleys far below sea level. Fjords are places of quiet beauty, where waterfalls tumble from cliffs, seabirds nest on precipitous ledges, and the water reflects the sky in shades of gray and blue. They are glaciers' gifts to the sea, landscapes shaped by ice but now ruled by water. Moraines are piles of debris left behind by glaciers. As glaciers move, they act like conveyor belts, carrying rocks, soil, and boulders plucked from the landscape. This debris accumulates in various places on and around the glacier. When the ice melts, the debris is deposited, forming moraines. Terminal moraines mark the farthest extent of a glacier, piles of unsorted material bulldozed to the front. Lateral moraines form along the glacier's sides, ridges of rock tracing where the ice once flowed. Medial moraines appear as dark stripes down the center of glaciers where two ice streams merge. After the glacier retreats, these moraines remain as visible evidence of past ice extent. They are often the first thing to revegetate, pioneering plants taking root in the raw mineral soil. Moraines are records, written in stone and dirt, telling stories of advance and retreat, of ice and time. Erratics are boulders transported far from their source by glaciers. Among the strangest features left by glaciers are erratics, large boulders resting in places where they clearly do not belong. These rocks may be made of granite sitting atop limestone, or basalt perched on sandstone, evidence that they traveled from elsewhere. Glaciers plucked these boulders from distant mountainsides and carried them, sometimes hundreds of kilometers, before depositing them when the ice melted. Erratics can be as small as pebbles or as large as houses. They puzzled geologists for centuries, until the concept of glaciation was accepted. In the 19th century, some thought erratics were deposited by biblical floods or floating icebergs. Only later did scientists realize that glaciers were the culprits. Today, erratics are valued clues in reconstructing past glaciations, tracing ice flow directions, and understanding landscape evolution. They are silent travelers, frozen in time at the end of their long journeys. Glaciers polish and scratch bedrock as they pass over it. Beneath a moving glacier, the bedrock is subjected to intense abrasion. Rocks embedded in the ice act like sandpaper, grinding and scratching the surface. The result is glacial polish, smooth expanses of bedrock that gleam when wet. Alongside the polish are glacial striations, parallel scratches carved by rocks dragged along the base. These features are often preserved long after the glacier has melted, providing evidence of past ice flow direction. In some places, entire mountainsides bear the marks of glaciation, smooth and striated, a testament to the grinding power of ice. Geologists use these features to reconstruct ancient glaciations, mapping the extent and movement of ice sheets that vanished thousands of years ago. The polished rock surfaces, often beautiful in their simplicity, are records of immense forces applied, patiently, over millennia. Hanging valleys occur where tributary glaciers join larger ones. When smaller glaciers flow into larger trunk glaciers, they join at the surface level of the ice. But glaciers erode at different rates depending on their size and thickness. The larger glacier carves its valley deeper than the smaller tributary. When the ice melts, the tributary valley is left suspended high above the main valley floor, creating a hanging valley. Water from these valleys often tumbles down as waterfalls, some of the most spectacular in the world. Yosemite's famous waterfalls, including Bridal Veil and Yosemite Falls, cascade from hanging valleys carved by tributary glaciers. These features are beautiful and geologically informative, illustrating the differential erosive power of ice. They are also reminders of the interconnectedness of glacier systems, where many streams of ice converge and interact, shaping landscapes in complex and lasting ways. Tarns are lakes that form in glacially carved basins. After glaciers retreat, they often leave behind depressions in the landscape, hollows carved by the ice's erosive action. When these basins fill with meltwater or precipitation, they become tarns, small lakes nestled in mountain cirques or valleys. Tarns are typically clear and cold, fed by snowmelt and rain. They are often surrounded by rocky, barren landscapes, only slowly being colonized by vegetation. Alpine hikers prize tarns for their beauty and tranquility, jewel-like waters reflecting peaks and sky. Ecologically, tarns are important habitats, supporting unique communities of aquatic life, adapted to cold, nutrient-poor conditions. They are also records of glaciation, their very existence proof that ice once occupied these spaces. To sit beside a tarn is to rest in a place shaped by ice, a quiet remnant of a colder time. Roches moutonnées are asymmetric rock formations sculpted by ice. As glaciers flow over bedrock, they create distinctive landforms, called roches moutonnées, a French term meaning sheep-like rocks, because of their smooth, rounded appearance. These features have a characteristic asymmetry, a gently sloping, smooth side facing the direction from which the ice came, and a steep, rough side on the downstream side. The smooth side is created by abrasion as the glacier slides over the rock, polishing it. The rough side results from plucking, where the glacier freezes onto the rock and tears chunks away as it moves. Roches moutonnées are common in glaciated terrains and provide clear evidence of ice flow direction. They are small in scale, often just a few meters high, but numerous, dotting landscapes that once lay beneath ice. They are elegant examples of how glaciers sculpt bedrock, creating beauty through the interplay of erosion and force. Glacier ice and color. Old glacier ice appears deep blue in crevasses and caves. The deeper you go into a glacier, the more intense the blue becomes. This is most visible in crevasses and ice caves, where light penetrates thick ice. The blue color is not from impurities, but from the ice itself. Dense, ancient ice absorbs longer wavelengths of light and scatters the shorter blue wavelengths. The effect is subtle in thin or young ice, but in thick accumulations, it is stunning. Ice caves, carved by meltwater flowing through or beneath the glacier, reveal walls and ceilings glowing with ethereal blue light. Photographers and adventurers seek these places out, drawn by the otherworldly beauty. The blue of glacier ice is the color of time compressed, of air squeezed out, of snow transformed through patience and pressure into something crystalline and luminous. Surface meltwater creates blue pools on glaciers in summer. During warmer months, the surface of many glaciers becomes dotted with meltwater pools, some small, others large enough to kayak across. These pools are often a brilliant turquoise or deep blue, contrasting sharply with the white ice around them. The color comes from the scattering of light by fine sediment suspended in the water and the absorption of longer wavelengths by the water itself. Meltwater pools are transient features, forming, draining, and reforming as the season progresses. They can drain suddenly if the water finds a route through cracks in the ice, creating moulins, vertical shafts that funnel water to the glacier's base. These pools are beautiful, but also significant for glacier dynamics, as they influence melting rates and ice movement. They are ephemeral paintings on the glacier's surface, redrawn each summer. Dirt and debris create dark streaks on glacier surfaces. Not all of a glacier's surface is pristine white or blue. Many glaciers are striped with dark bands of rock, soil, and organic material. These streaks, called medial moraines, form where tributary glaciers merge, carrying debris from their respective valleys. The debris absorbs more heat than clean ice, causing differential melting and creating ridges. Supraglacial debris, material on top of the glacier, can also come from rockfall or wind-blown dust. In some glaciers, the surface is so covered with debris that the ice beneath is barely visible. These debris-covered glaciers melt more slowly because the overlying material insulates the ice. The dark streaks and patches add texture and pattern to the glacier, making each one visually unique. They are also records of the glacier's journey, traceable to specific source areas in the surrounding mountains. Some glacier ice contains ancient pollen and plant material. Trapped within glacial ice are not just air bubbles and dust, but also biological material. Pollen grains, spores, seeds, and even fragments of plants can be frozen into the ice, preserved for centuries or millennia. When scientists extract ice cores, they analyze this material to reconstruct past vegetation and climate. A layer containing pine pollen might indicate a warmer period when forests grew at higher elevations. Grass pollen might suggest cooler, drier conditions. This biological archive is delicate and detailed, offering glimpses into ecosystems that no longer exist. It also connects the frozen world of glaciers to the living world of plants and forests, showing how ice, life, and climate are intertwined. The pollen is microscopic, invisible to the naked eye, but its presence in the ice is a reminder that glaciers capture more than just water. They hold fragments of the biosphere itself. Red algae can tint snow and ice with pink or red hues, In some glacial environments, especially during summer, snow and ice take on surprising colors. Pink, red, or even orange patches appear, looking almost like watermelon snow. This is caused by snow algae, microscopic organisms that thrive in cold, sunlit conditions. The most common is Chlamydomonas nivalis, which produces a red pigment to protect itself from intense ultraviolet radiation at high elevations. The algae bloom on the surface of snow and ice, creating colorful patches that can extend for meters. While beautiful, the algae also have a practical effect. They darken the snow, reducing its reflectivity and increasing melting. This creates a feedback loop, where more melting provides more liquid water, which supports more algae growth. Snow algae are a reminder that even in the coldest environments, life finds a way, adding unexpected color to the monochrome world of ice. Bubbles in ice capture ancient air, creating white bands. When you look closely at glacier ice, you may see it is not uniformly clear. Instead, it contains countless tiny bubbles, giving parts of the ice a white or cloudy appearance. These bubbles are trapped air from when the snow first fell and compacted. In young, shallow ice, the bubbles are large and irregularly shaped. Deeper down, under more pressure, they become smaller and more spherical. These bubbles are scientifically valuable, containing samples of ancient atmosphere that can be analyzed for composition. But they also affect the ice's appearance, scattering light and creating the white bands and zones that give some glaciers a layered look. Where the ice is very old and the bubbles have been largely compressed out, the ice becomes clear and takes on a deep blue color. The presence or absence of bubbles is thus a marker of age and depth. Icebergs carved from glaciers float with most of their mass underwater. When chunks of ice break off from tidewater glaciers or ice shelves, they become icebergs, drifting in the ocean. What is visible above the water is only a fraction of the berg's total volume, typically about 1/8 to 1/9. The rest lurks beneath the surface, hidden but massive. This is why icebergs are dangerous to ships. Their true size is concealed. The ice is less dense than seawater, which is why it floats, but only barely. The saying "tip of the iceberg" comes from this reality, where the visible portion hints at a much larger hidden mass. Icebergs come in many shapes: tabular, blocky, wedge-shaped, or pinnacled, depending on how they carved and how they have melted. They can drift for years, carried by ocean currents thousands of kilometers from their origin, slowly melting and shrinking until they disappear entirely. Glaciers and climate. Glaciers are sensitive indicators of climate change. Because glaciers exist at the threshold between freezing and melting, they respond quickly to changes in temperature and precipitation. A small shift in average temperature can mean the difference between growth and retreat. This makes glaciers excellent indicators of climate change, natural thermometers recording the planet's warming or cooling. Scientists monitor glacier mass balance, the difference between accumulation and melting, to track climate trends. Around the world, the vast majority of glaciers are currently retreating, losing mass and withdrawing to higher elevations. This is consistent evidence of global warming. The rate of retreat has accelerated in recent decades, visible in photographs taken years apart, showing dramatic ice loss. Glaciers do not lie. They cannot be influenced by politics or opinion. They simply respond to the physical conditions around them, making them invaluable witnesses to our changing climate. Ice cores from glaciers reveal climate history spanning hundreds of thousands of years. Deep ice cores extracted from glaciers and ice sheets are among the most important tools in climate science. By drilling down through kilometers of ice, scientists retrieve continuous records of Earth's climate stretching back 800,000 years or more. Each layer of ice corresponds to a year or season of snowfall, and the chemical composition of that ice holds information about temperature, atmospheric gases, volcanic eruptions, and even solar activity. Isotopes of oxygen and hydrogen in the ice reveal past temperatures. Air bubbles contain ancient atmosphere. Dust and pollen tell stories of wind, patterns, and vegetation. These cores have shown that Earth's climate has varied dramatically over time, with ice ages and warm periods cycling in response to orbital variations and greenhouse gas levels. They provide context for current warming, showing that recent changes are rapid and unprecedented in the historical record. The last ice age covered much of North America and Europe in ice. About 20,000 years ago, at the peak of the most recent ice age, vast ice sheets covered regions that are now temperate. The Laurentide ice sheet buried Canada and extended south into the northern United States, reaching as far as present-day New York, Ohio, and Montana. The Scandinavian ice sheet covered northern Europe. These ice sheets were thousands of meters thick, holding so much water that global sea level was about 120 meters lower than today. Coastlines extended far beyond their current positions. Land bridges connected continents. The weight of ice depressed the Earth's crust. The climate was cold and dry, with tundra and grasslands where forests now grow. Then, starting around 18,000 years ago, the climate warmed. The ice sheets began to retreat, melting back over thousands of years. By 10,000 years ago, they had shrunk to roughly their present extent. This transition marked the end of the Pleistocene epoch and the beginning of the Holocene, the current interglacial period in which human civilization has flourished. Retreating glaciers expose landscapes unseen for thousands of years. As glaciers withdraw, they reveal the land they once covered, landscapes that have been hidden beneath ice for millennia. These newly exposed areas are raw and fresh, polished bedrock, piles of moraine, and barren ground devoid of soil. Sometimes, remarkably preserved artifacts emerge from the ice. In alpine regions, hikers have discovered ancient tools, clothing, and even human remains, such as Ötzi the Iceman, a 5,300-year-old mummy found in the Alps. Forests that grew before the ice, advanced, are revealed as stumps and logs, still intact after thousands of years in cold storage. These discoveries provide glimpses into past climates and human activity. They are poignant reminders of time's passage and the cycles of cold and warmth that shape the planet. The landscapes emerging from beneath retreating glaciers are new, yet ancient, blank canvases that nature will slowly repaint. Melting glaciers contribute to rising sea levels. One of the most significant consequences of glacier retreat is the contribution to sea level rise. As glaciers and ice sheets melt, the water flows into the ocean, adding volume and raising sea levels globally. Small mountain glaciers have been contributing to sea level rise for over a century. More recently, the great ice sheets of Greenland and Antarctica have begun losing mass at accelerating rates. Greenland alone is now losing around 280 billion tons of ice per year. Antarctica's loss is harder to measure, but also substantial. Together, with thermal expansion of seawater as it warms, glacier melt is driving sea level rise that threatens coastal communities, ecosystems, and infrastructure. Low-lying islands and coastal cities face increasing risks of flooding. The process is slow on human timescales, but inexorable. Even if warming were to stop today, glaciers would continue adjusting for decades or centuries, releasing the water they have held for so long. Glaciers reflect sunlight, helping to cool the planet. Glaciers and ice sheets are bright, reflecting much of the sunlight that strikes them. This high reflectivity, called albedo, plays an important role in Earth's energy balance. Ice reflects 80 to 90% of incoming solar radiation back to space, preventing that energy from being absorbed and warming the planet. Oceans and forests, by contrast, absorb most sunlight, warming the surface. When glaciers melt and expose darker surfaces like rock, soil, or water, the albedo decreases and more heat is absorbed. This creates a feedback loop. Warming melts ice, which reduces reflectivity, which causes more warming, which melts more ice. This is called the ice albedo feedback, and it amplifies climate change, particularly in polar regions. The bright white of glaciers is not just beautiful, it is functionally important, a cooling mechanism that helps stabilize climate. As ice disappears, that cooling effect diminishes. Permafrost beneath glaciers can store ancient carbon. Beneath many glaciers, especially in polar regions, lies permafrost, permanently frozen ground that can be thousands of years old. This permafrost contains organic matter, dead plants and animals that accumulated over millennia and were frozen before they could decay. Locked within this frozen ground is carbon, stored safely as long as temperatures remain below freezing. But as glaciers retreat and temperatures rise, permafrost begins to thaw. When it does, microbes awaken and begin decomposing the organic matter, releasing carbon dioxide and methane into the atmosphere. This is another feedback loop. Warming thaws permafrost, which releases greenhouse gases, which causes more warming. The amount of carbon stored in permafrost is enormous, potentially rivaling the carbon in Earth's atmosphere. The fate of this frozen carbon is one of the great uncertainties in climate science, and it is tied intimately to the fate of glaciers that have kept it frozen. Glacial meltwater feeds rivers relied upon by millions of people. Many of the world's great rivers are fed, in part or entirely, by glacier meltwater. In the dry season, when rainfall is scarce, glaciers act as reservoirs, releasing stored water gradually. The Ganges, fed by Himalayan glaciers, sustains hundreds of millions of people in India and Bangladesh. The Indus, Brahmaputra, Yellow, and Yangtze rivers also depend on glacial sources. In South America, glaciers in the Andes provide water to cities like Lima and La Paz. As glaciers shrink, this reliable water supply becomes less certain. Initially, melting glaciers can increase river flow, but eventually, as the ice is exhausted, flow will decrease, potentially leading to water shortages. Communities that have depended on glacial meltwater for agriculture, drinking, and hydropower face an uncertain future. The retreat of glaciers is not just an environmental issue but a human one, affecting livelihoods, food security, and geopolitical stability. Life around glaciers. Glaciers create unique ecosystems at their margins. The edges of glaciers are dynamic environments where ice meets rock, soil, and water. These marginal zones are harsh but not lifeless. As glaciers retreat, they leave behind freshly exposed ground, and pioneer species quickly colonize. Mosses and lichens are often first, followed by grasses and shrubs. Streams of meltwater provide moisture, creating ribbons of green in otherwise barren landscapes. Animals venture into these areas to feed. Birds, insects, and mammals like mountain goats or ibex. The ecosystem is simple but resilient, adapted to cold, short growing seasons and unstable substrate. These marginal zones are also laboratories for ecological succession, where scientists can observe how life reclaims land. They are places of transition, neither fully ice nor fully living landscape, but something in between, constantly shifting as the glacier advances or retreats. Iceworms live on the surface of some glaciers. In a remarkable adaptation to extreme cold, certain species of segmented worms live their entire lives on glacier surfaces. These iceworms, primarily species of the genus Mesenchytreus, are found on glaciers in North America, especially in Alaska and the Pacific Northwest. They are small, dark, and emerge at dawn and dusk to feed on algae, pollen, and other organic material that accumulates on the ice. During the heat of the day, they burrow into the ice to avoid temperatures that would be lethal to them. Iceworms cannot survive above a few degrees Celsius. Warmth kills them quickly. Their metabolism is adapted to function at temperatures just below freezing. They are among the few animals that spend their entire lives on ice, a testament to life's ability to exploit even the most extreme environments. To find them, one must look closely, for they are small and blend with shadows, but they are there, thriving where few would expect. Algae blooms on glaciers can darken the ice. Glaciers are not sterile. In the right conditions, microscopic algae thrive on their surfaces, particularly during summer. These algae, including species like Anselenema, form blooms that can darken large areas of ice, from white to gray or even black. This darkening reduces the glacier's albedo, causing it to absorb more sunlight and melt faster. Scientists call this a biological albedo feedback. The algae themselves are adapted to intense ultraviolet radiation and freezing temperatures, producing pigments that protect. While individually microscopic, collectively they can alter the appearance and behavior of entire glaciers. Research into glacier algae is relatively recent, and scientists are still learning how widespread and significant these blooms are. But it is clear that glaciers are not simply physical systems. They are ecosystems, inhabited and influenced by living organisms that in turn influence the ice itself. Glacial streams are cold, silty, and nutrient-poor, but support specialized life. Water flowing from glaciers is distinctive, cold, milky with suspended sediment, and low in nutrients. These glacial streams are challenging environments for life. The cold water holds more oxygen, but the silt reduces light penetration, making photosynthesis difficult for aquatic plants. The flow is highly variable, surging during warm afternoons and slowing at night. Despite these challenges, specialized organisms thrive. Certain species of stoneflies, mayflies, and midges have adapted to these conditions, spending their larval stages in glacial streams. These insects, in turn, support fish, birds, and other predators. Glacial streams also transport sediments and nutrients downstream, influencing ecosystems far from the ice. As glaciers retreat, the character of these streams changes, warming and clearing, which can disrupt the species adapted to cold, silty conditions. These streams are dynamic interfaces between ice and life. Birds nest near glaciers, relying on meltwater and insects. In the brief summer season, the areas around glaciers come alive with birds. Species like snowbuntings, ptarmigan, and alpine choughs are drawn to the vicinity of ice, where meltwater creates wetlands and insects emerge in abundance. These birds nest on rocky outcrops and moraines, raising their young quickly to take advantage of the short season. The meltwater streams attract insects, which in turn attract insectivorous birds. Raptors soar overhead, hunting for small mammals on the prizous tundra. The presence of ice influences the entire food web, providing water and moderating local climate. In some regions, Migratory birds time their arrival to coincide with peak insect emergence near glaciers. These avian visitors are part of the glacier's extended ecosystem, their lives intertwined with the rhythms of ice and melt. Glaciers grind rock into fine flour that nourishes downstream ecosystems. As glaciers move, they erode bedrock into extremely fine particles, so fine they remain suspended in meltwater, giving glacial streams their characteristic milky appearance. This sediment is called glacial flour or rock flour. While it clouds the water, it is also rich in minerals. When deposited in river deltas, floodplains, or the ocean, it provides nutrients that support plant growth and primary productivity. In coastal regions, glacial flour settling in the ocean can stimulate phytoplankton blooms, the base of the marine food web. This nutrient delivery is one of the subtle ways glaciers support life far from their icy reaches. As glaciers retreat, the production of rock flour may change, potentially affecting downstream ecosystems that have relied on this mineral input for millennia. The fine dust of ground stone is more than debris. It is fertility, dispersed by ice and water. Some fish species are specially adapted to cold glacial rivers. In glacial rivers and lakes, certain fish species thrive in conditions that would be hostile to most. These cold water specialists, such as Arctic char, dolly varden, and certain species of trout, have adaptations that allow them to survive in near-freezing water. Their metabolism functions efficiently at low temperatures, and they can tolerate the high turbidity and variable flows characteristic of glacial systems. Some spawn in clear tributaries but feed in the main glacial rivers, taking advantage of the insects and organic matter carried by the flow. Indigenous peoples in glaciated regions have depended on these fish for food for thousands of years. As climate warms and glaciers retreat, these fish face uncertain futures. Warmer water, reduced flow, and changes in habitat could favor other species, potentially outcompeting the cold-adapted specialists. These fish are living connections to the Ice Age, adapted to a world shaped by glaciers. Glaciers in culture and history. Indigenous peoples have lived alongside glaciers for millennia. Long before glaciers became subjects of scientific study, they were part of the landscapes inhabited by indigenous communities. In the Andes, the Himalayas, Alaska, the Alps, and elsewhere, people developed rich cultural relationships with ice. Glaciers were sacred, associated with deities and spirits. They provided water, influenced weather, and marked territorial boundaries. Some communities harvested ice for trade or cooling. Stories and place names reflect the presence of ice in the cultural landscape. For many indigenous groups, glaciers are not just physical features, but living entities, deserving respect and care. As glaciers retreat in the modern era, these communities often feel the loss most acutely, not only because of practical impacts on water supply, but also because of the cultural and spiritual significance of the ice. Their knowledge of glaciers, accumulated over generations, is now recognized as valuable by scientists seeking to understand long-term changes. Explorers once crossed glaciers in search of roots and knowledge. The age of exploration brought adventurers into glaciated regions, seeking new routes, resources, and understanding. In the 18th and 19th centuries, European explorers ventured into the Alps, mapping glaciers and attempting dangerous crossings. In the polar regions, expeditions sought passages through ice-choked seas and traversed ice sheets in epic journeys of endurance. Names like Shackleton, Amundsen, Scott, and Nansen are associated with glacial exploration, their stories of survival and discovery etched into history. These explorers faced crevasses, blizzards, starvation, and cold, yet they were driven by curiosity and ambition. Their accounts brought glaciers into public consciousness, inspiring both awe and scientific interest. The challenges they faced highlighted the power and indifference of ice, environments where human will was tested against nature's extremes. Their legacies remain in the maps they made and the knowledge they gathered, much of it at great cost. Early scientists debated whether ice ages had once covered the Earth. In the early 19th century, geologists noticed puzzling features in the landscape: erratic boulders, U-shaped valleys, polished bedrock, all far from any existing glaciers. Some proposed catastrophic floods or floating icebergs as explanations, but a few, including Swiss scientist Louis Agassiz, argued that vast ice sheets had once covered much of Europe and North America. This Ice Age theory was controversial, challenging prevailing beliefs. Agassiz traveled widely, presenting evidence and convincing skeptics. By the late 1800s, the Ice Age theory was accepted, revolutionizing geology and paleontology. It explained not only landforms but also the distribution of fossils and the extinction of species like mammoths. The realization that Earth's climate had changed dramatically in the past opened new questions about what drove these changes and whether they could happen again. It was a paradigm shift, reshaping how humans understood their planet's history. Glaciers have been worshipped and feared across cultures. In many societies, glaciers were seen as powerful, even supernatural. In the Andes, glaciers were considered apus, sacred mountain spirits that provided water and protection. Offerings were made to appease them. In Tibetan Buddhism, glaciers and high peaks are associated with deities and spiritual power. In Norse mythology, ice and frost played central roles in creation myths. Alpine communities in Europe sometimes viewed glaciers with fear, believing that advancing ice could destroy villages, a fear not entirely unfounded during the Little Ice Age, when some glaciers did advance, overrunning farmland. These cultural attitudes reflect the lived experience of people for whom glaciers were immediate and influential presences. The ice was both giver and taker, provider of water, but also a force of destruction. These beliefs remind us that glaciers are not just physical phenomena, but also cultural ones, woven into the stories and spirituality of countless communities. Artists and writers have long been inspired by glaciers. The Romantic movement of the 18th and 19th centuries brought artists and poets to the Alps and other glaciated regions, seeking sublime landscapes that inspired awe and terror. Painters like Caspar David Friedrich and J.M.W. Turner depicted glaciers and icy peaks, capturing their grandeur and mystery. Writers like Mary Shelley set crucial scenes of Frankenstein on glaciers, using ice as a symbol of desolation and beauty. John Muir, the American naturalist, wrote eloquently about glaciers in the Sierra Nevada and Alaska, describing their beauty and their role in shaping the land. In the 20th and 21st centuries, photographers and filmmakers have continued this tradition, documenting glaciers in stunning detail. These artistic representations have shaped public perceptions of glaciers, presenting them as sublime, threatened, and worthy of preservation. Art connects people emotionally to landscapes they may never see in person, fostering a sense of shared heritage and responsibility. Glaciers have been sites of scientific discovery and adventure. Glaciers have drawn scientists from many fields: glaciologists studying ice dynamics, climatologists extracting ice cores, biologists discovering extremophile organisms, and geologists examining glacial landscapes. Fieldwork on glaciers is challenging, requiring physical endurance, technical skills, and tolerance for cold and isolation. Yet it is also exhilarating, offering the chance to work in some of Earth's most pristine environments. Discoveries made on glaciers have profoundly advanced our understanding of climate change, past climates, ice dynamics, and even astrobiology. Research stations on ice sheets operate year-round, staffed by dedicated scientists. Expeditions to remote glaciers push the boundaries of logistics and technology. This scientific work is motivated by curiosity but also by urgency, as the subjects of study are changing rapidly. Glaciers are both archives of the past and indicators of the future, and the work being done on them now is critical to understanding both. The sounds of ice glaciers creak and groan as they move. Glaciers are not silent. As the ice deforms and flows, it produces sounds, creaks, groans, pops, and cracks. These sounds are caused by stress within the ice, as crystals shift and fracture. On a quiet day, near a glacier, you can hear these noises, eerie and otherworldly, as if the ice itself is speaking. The sounds can be sudden and sharp, like a gunshot, or low and rumbling, almost subsonic. They remind listeners that glaciers are dynamic, constantly in motion even when they appear still. Scientists sometimes use the sounds glaciers make, recorded with seismometers, to study internal processes and detect events like crevasse formation or basal sliding. For visitors, the sounds add to the glacier's mystique, a soundtrack to the frozen landscape that hints at the immense forces at work beneath the surface. Carving icebergs produce thunderous roars. One of the most dramatic sounds in nature is the carving of an iceberg. When a large chunk of ice breaks away from a glacier front and crashes into the water, the noise is like thunder, echoing across valleys and fjords. The roar is followed by the splash and the grinding of ice fragments. Watching and hearing carving is unforgettable, a visceral demonstration of the glacier's power. The sound can be heard from kilometers away, a deep rumble that vibrates through the ground. For those fortunate enough to witness it, the moment is both thrilling and humbling. It is a reminder of the scale of glaciers and the forces that drive them. Each carving event is unique, unpredictable, and brief, a spectacle of ice and water that has occurred for millions of years and continues today. Meltwater streams create trickling, rushing soundscapes. During the melt season, glaciers are alive with the sound of water. Streams trickle, rivulets rush, and rivers roar as meltwater flows over, through, and beneath the ice. The soundscape changes with the time of day. In the morning, the flow is subdued. By afternoon, as the sun warms the ice, the flow increases and the sounds intensify. Water cascades down crevasses, gurgles through moulins, and emerges at the glacier's terminus in powerful torrents. These sounds are soothing, a natural symphony of water finding its way downhill. They are also signs of the glacier's activity, evidence of melting and movement. For campers near glaciers, the sound of meltwater is a constant companion, a reminder of the dynamic processes shaping the ice and the landscape around it. Wind howling across ice fields is both haunting and beautiful. In glaciated regions, especially on ice sheets and high plateaus, the wind can be relentless. It sweeps across the ice with nothing to slow it, creating a howling, whistling sound that is both haunting and beautiful. The wind picks up fine snow and ice particles, creating ground blizzards that reduce visibility to near zero. The sound is constant, filling the air, and can be disorienting. For those who live or work on ice sheets, the wind is a defining feature of the environment, shaping daily routines and requiring constant vigilance. Yet there is a stark beauty to it, the primal sound of air moving across an empty, frozen expanse. It is the voice of the ice desert, powerful and indifferent, a reminder of the raw forces that govern polar regions. Glaciers, and the future most glaciers worldwide, are currently retreating. The evidence is clear and widespread. The vast majority of the world's glaciers are shrinking. From the Himalayas to the Andes, from Alaska to the Alps, glaciers are losing mass and retreating to higher elevations. This retreat is documented through satellite imagery, repeat photography, and field measurements. The rate of retreat has accelerated in recent decades, correlated with rising global temperatures. Some small glaciers have disappeared entirely, melting away within a human lifetime. The retreat is not uniform. A few glaciers in certain regions are stable or even advancing, often due to local factors like increased snowfall. But overall, the trend is unmistakable. Glaciers are responding to a warming climate, and their retreat is one of the most visible signs of environmental change. It is a global phenomenon, transcending borders and create politics written in ice for anyone to see. Some glaciers may disappear within decades. In many mountain ranges, smaller glaciers are projected to vanish within the next few decades if current warming trends continue. The glaciers of Glacier National Park in Montana, which numbered around 150 inches the mid-19th century, have dwindled to fewer than 30, and many of those are small and fragile. Scientists predict most will be gone by mid-century. Similarly, glaciers in the European Alps, the Pyrenees, and tropical mountains like those in East Africa are shrinking rapidly. These losses are not abstract. They represent the disappearance of landscapes, water sources, and ecosystems. For communities and ecosystems that depend on these glaciers, the impacts are profound. The loss of glaciers also means the loss of climate archives. Once melted, the information contained in the ice is gone forever. These disappearances are wake-up calls, urgent reminders of the pace of change and the irreversibility of some losses. Ice sheet collapse could reshape coastlines for millennia. While mountain glaciers receive much attention, the most consequential ice masses are the ice sheets of Greenland and Antarctica. These hold enough water to raise sea levels by tens of meters. If they were to collapse, the impacts would be catastrophic, inundating coastal cities, displacing hundreds of millions of people, and altering coastlines for thousands of years. Current models suggest that parts of these ice sheets are vulnerable to accelerated melting and collapse, particularly in West Antarctica, where much of the ice rests on bedrock below sea level. Once retreat begins in such settings, it can become self-reinforcing, leading to rapid ice loss. The timescales are uncertain, decades to centuries, but the potential consequences are profound. Understanding the stability of ice sheets is one of the most important and urgent questions in climate science. Scientists are monitoring glaciers to understand climate impacts. Around the world, researchers are measuring glaciers with increasing precision and frequency. They use satellite remote sensing, aerial photography, ground-based surveys, and automated weather stations to track changes in ice extent, thickness, and velocity. Ice cores are drilled to reconstruct past climates. Meltwater is sampled to understand hydrology. Models simulate future glacier behavior under different climate scenarios. This work is painstaking and often dangerous, requiring fieldwork in harsh environments. But it is essential. Glaciers are indicators of climate change, and understanding their response helps scientists predict future impacts on water resources, sea level, and ecosystems. The data collected from glaciers is integrated into global climate models, improving our ability to forecast and prepare for change. This monitoring is a global effort involving scientists from many nations, all working to understand the fate of ice in a warming world. Efforts to protect glaciers include reducing greenhouse gas emissions. The primary driver of glacier retreat is global warming, caused by greenhouse gas emissions from burning fossil fuels, deforestation, and other human activities. Protecting glaciers, therefore, requires addressing the root cause, reducing emissions. International agreements like the Paris Agreement aim to limit warming and slow the impacts on glaciers and other climate-sensitive systems. Transitioning to renewable energy, increasing energy efficiency, protecting forests, and changing consumption patterns are all part of the solution. Some propose geoengineering solutions, like shading glaciers with reflective materials, but these are experimental and address symptoms rather than causes. Ultimately, the fate of glaciers is tied to humanity's willingness to change course, to reduce the carbon footprint, and embrace sustainability. The glaciers themselves cannot act. Their future depends entirely on the choices people make in the coming years and decades. Some communities are adapting to glacier loss. In regions where glacier retreat is already having impacts, communities are adapting in various ways. Farmers are changing crops, shifting to varieties that require less water, or irrigating more efficiently. Engineers are building reservoirs to store meltwater during periods of abundance. Hydropower operators are adjusting to changing river flows. Some communities are even relocating, moving away from areas prone to glacial lake outburst, floods, or other hazards. These adaptations are often costly and challenging, requiring resources and planning. They also highlight the inequities of climate change. Communities that have contributed least to emissions often face the greatest impacts and have the fewest resources to adapt. Despite the challenges, resilience and ingenuity are evident. People are finding ways to cope, drawing on traditional knowledge and modern technology. These adaptations are not ideal solutions, but they are necessary responses to a changing world. Glaciers remind us of Earth's dynamic climate history. Standing before a glacier, it is easy to feel a connection to deep time. The ice beneath your feet may have fallen as snow centuries ago, during a colder era. The valley carved by the glacier speaks to even older ice ages when ice covered vast areas. Glaciers are physical manifestations of climate, records of cold periods and warm interglacials. They remind us that Earth's climate has always changed, though the current pace and cause are unique. Understanding past climate variability, recorded in ice and glacial landscapes, provides context for present changes. It shows that glaciers have grown and shrunk many times, responding to natural cycles driven by orbital variations, volcanic eruptions, and other factors. But it also shows that current warming is rapid and driven by human actions. Glaciers bridge past and present, reminding us of where we have been and warning us about where we are going. Glacial hazards, glacial lake outburst floods, can devastate valleys downstream. As glaciers retreat, they often leave behind lakes dammed by moraines or ice. These glacial lakes can be unstable. If the dam fails, whether due to erosion, an earthquake, or the carving of ice, the lake can drain catastrophically. The resulting flood, called a glacial lake outburst flood or GLOF, sends a torrent of water, ice, and debris racing down the valley. These floods can be devastating, destroying infrastructure, farmland, and settlements. They have caused loss of life and displacement of communities in the Himalayas, the Andes, and other glaciated regions. The risk is increasing as warming leads to more and larger glacial lakes. Monitoring and early warning systems are being developed and some high-risk lakes have been drained or stabilized. But the hazard remains, a dangerous legacy of glacier retreat, where ice and water combine in sudden, violent releases. Crevasses pose deadly risks to those crossing glaciers. Crevasses are deep cracks in glacier ice, formed where the ice is under tension. They can be narrow or wide, shallow or plunging tens of meters into darkness. Snow can bridge crevasses, hiding them from view, creating deadly traps for the unwary. Mountaineers and glaciologists travel roped together when crossing glaciers, so if one person falls into a hidden crevasse, others can arrest the fall. Despite precautions, accidents happen. Crevasses have claimed the lives of explorers, researchers, and adventurers. The danger is real and immediate. Yet, with proper training and equipment, travel on glaciers can be done safely. Crevasses are part of the glacier's nature, evidence of its movement and stress. They demand respect and caution, reminding us that glaciers are not passive landscapes, but active, dynamic, and sometimes dangerous. Avalanches can be triggered by glacier movement or collapse. Glaciers and avalanches are intimately connected. Steep glaciers or hanging ice can collapse without warning, triggering massive ice avalanches that roar down mountainsides. These avalanches can travel at high speeds, carrying ice blocks the size of buildings. They can bury valleys, destroy forests, and threaten communities. Climate change is increasing avalanche risk in some areas as warming destabilizes ice. In mountainous regions, avalanche forecasting and monitoring are critical for safety. Some avalanches have become famous, like the 1970 Huascarán avalanche in Peru, which buried the town of Yungay and killed thousands. Others occur in remote areas, witnessed only by wildlife or not at all. Avalanches are reminders of the power of ice in motion, gravity pulling frozen water downward with catastrophic force. Respect for this hazard is essential for anyone living or traveling in glaciated mountains. Melting glaciers can release long-buried pollutants. Glaciers are not pristine. Glaciers accumulate whatever falls on them, including pollutants. For decades or centuries, industrial pollutants, pesticides, radioactive particles, and other contaminants have been deposited on glaciers through atmospheric transport. These substances become trapped in the ice, sequestered and immobile. But as glaciers melt, they release what they have stored. Studies have found elevated levels of mercury, PCBs, and other toxins in meltwater and downstream ecosystems. This release is an unintended consequence of glacier retreat, a legacy of past pollution coming back as ice disappears. It poses risks to water quality and wildlife. The phenomenon illustrates how interconnected environmental issues are. Pollution from one era and place can reappear far away and much later, delivered by melting ice. Glaciers, in this sense, are both archives and time bombs, holding the past until it is released into the present. Glaciers in extreme environments. Antarctica's glaciers flow into the coldest, driest desert on Earth. Antarctica is a land of extremes, the coldest, windiest, and driest continent. Yet, it is almost entirely covered by ice, a vast ice sheet that flows slowly toward the coasts. Despite the extreme cold, glaciers here move, driven by the sheer weight of accumulated snow. The interior of Antarctica receives very little precipitation, making it technically a desert. But what does fall never melts, accumulating over hundreds of thousands of years. Temperatures can drop below -80 degrees Celsius, cold enough to freeze carbon dioxide out of the air. In this environment, glaciers are both the dominant feature and the defining characteristic. They create a landscape of white emptiness, where horizons blur and perspective is lost. It is one of the most alien environments on Earth, yet it holds clues to our planet's past and future, locked in its ancient ice. Greenland's ice sheet is the second largest in the world. Greenland is mostly covered by a vast ice sheet that rises over 3,000 meters at its highest point. This ice sheet contains enough water to raise global sea levels by about 7 meters. Like Antarctica, the ice flows from the interior toward the coasts, where it carves into the ocean or melts. Greenland's ice sheet is losing mass rapidly, contributing significantly to current sea level rise. The edges of the ice sheet are dotted with research stations where scientists study ice dynamics, climate history, and microbial life. Indigenous Inuit communities live along the coasts, their lives intertwined with the ice. For thousands of years, the ice has been stable, but now it is changing, melting faster than at any time in recorded history. Tropical glaciers exist near the equator at high elevations. It seems contradictory, but glaciers exist in tropical regions, perched on the highest mountains, where elevation creates cold despite proximity to the equator. The glaciers of Mount Kilimanjaro in Tanzania, the Ruwenzori Mountains in Uganda, and the high Andes of Ecuador, Peru, and Bolivia are examples. These glaciers are small and particularly vulnerable to warming because temperatures at tropical high elevations are close to the melting point. Even slight warming can tip the balance. Many tropical glaciers have lost significant mass or disappeared entirely in recent decades. Their loss affects water supplies for communities that depend on glacier meltwater during dry seasons. These glaciers are also scientifically valuable, providing climate records from the tropics that complement those from polar regions. Their existence is a reminder that ice can form anywhere conditions are right, and their disappearance is a stark indicator of global warming. Patagonian ice fields stretch across Argentina and Chile. In southern South America, the Patagonian ice fields are among the largest temperate ice masses outside polar regions. The northern and southern Patagonian ice fields together cover thousands of square kilometers, feeding dozens of glaciers that flow into fjords, lakes, and rivers. The climate here is maritime, with heavy precipitation that sustains the ice. These glaciers are spectacular, with some, like Perito Moreno Glacier, famous for their dramatic carving events. The region is remote, sparsely populated, and stunningly beautiful, with turquoise lakes and jagged peaks. Scientists study these ice fields to understand glacier dynamics in temperate climates and to track changes over time. Tourism has grown, bringing visitors to witness the majesty of glaciers before they change further. The Patagonian ice fields are treasures of the southern hemisphere, vast and wild. Glaciers on high peaks in the Himalayas feed major Asian rivers. The Himalayas, the world's highest mountain range, are heavily glaciated, with thousands of glaciers clinging to peaks and valleys. These glaciers are the source of major rivers, including the Ganges, Indus, Brahmaputra, and Mekong, which support over 1 billion people. The glaciers act as water towers, storing precipitation as ice and releasing it gradually. This is especially important during the dry season, when other water sources are scarce. However, Himalayan glaciers are retreating rapidly, raising concerns about future water security. The region is also seismically active, and glacier retreat can create unstable glacial lakes, increasing flood risk. The Himalayas are culturally and spiritually significant, with glaciers and peaks considered sacred. The fate of these glaciers is tied to the well-being of a vast population, making their study and protection critical. Glacier research and exploration scientists drill ice cores to sample ancient ice layers. One of the most important techniques in glaciology is ice core drilling. Using specialized equipment, researchers drill vertically through a glacier or ice sheet, extracting a continuous cylinder of ice. These cores can be hundreds or thousands of meters long, representing tens or hundreds of thousands of years of accumulation. Once extracted, the cores are carefully transported to laboratories, where they are analyzed. Scientists measure isotopes, gases, dust, pollen, and other properties, building detailed records of past climate. The work is technically challenging, requiring precision and patience. In Antarctica and Greenland, drilling camps operate in extreme conditions, with teams working through long polar summers. The ice cores they retrieve are among the most valuable climate archives on Earth, providing data that inform our understanding of natural climate variability and the human impact on the atmosphere. Glaciologists use radar to map ice thickness and bedrock beneath glaciers. To understand a glacier fully, scientists need to know not just what is visible on the surface, but also what lies beneath. Ground-penetrating radar sends radio waves into the ice, which reflect off layers within the ice and off the bedrock at the base. By analyzing the returned signals, researchers can map the glacier's internal structure and measure its thickness. This technique has revealed subglacial mountains, valleys, and lakes hidden beneath kilometers of ice. It has shown that some glaciers rest on bedrock far below sea level, making them vulnerable to retreat. Radar surveys are conducted on foot, from snowmobiles, from aircraft, and even from satellites. The resulting maps are essential for modeling glacier behavior and predicting future changes. They turn glaciers from opaque white surfaces into three-dimensional landscapes understood in detail. Remote sensing satellites monitor glaciers from space. Modern glacier research relies heavily on satellites that orbit Earth, continuously observing ice from above. Instruments measure ice extent, surface elevation, movement, and temperature. Over decades, these observations have documented glacier retreat, ice sheet thinning, and accelerating flow. Satellites provide a global perspective, tracking glaciers in remote regions that are difficult or impossible to access on the ground. They also enable comparisons across different regions and time periods. Data from satellites like Landsat, ISAT, and the European Space Agency's Sentinel missions have been critical in demonstrating the scale and speed of glacier change. This technology has transformed glaciology, making it possible to monitor thousands of glaciers simultaneously and detect changes that would otherwise go unnoticed. The view from space reveals the planet as a whole, showing how interconnected ice, ocean, and atmosphere truly are. Automated weather stations on glaciers record conditions year-round. Understanding glacier behavior requires knowing the conditions they experience. Automated weather stations are installed on glaciers to measure temperature, wind speed, humidity, solar radiation, and precipitation. These stations operate year-round, even through harsh winters when human presence is impossible. The data they collect is transmitted via satellite to researchers, providing continuous records of the environment. This information is used to calculate glacier mass balance, understand melt rates, and validate climate models. Installing and maintaining these stations is challenging, requiring expeditions to remote, high-altitude locations. But the data they provide is invaluable, filling gaps in our knowledge and enabling more accurate predictions. These silent sentinels, perched on ice in some of the world's most extreme environments, quietly gather the information needed to understand a changing planet. Glaciers are studied by interdisciplinary teams of scientists. Glaciology is inherently interdisciplinary, drawing on physics, chemistry, biology, geology, climatology, and engineering. A single research project might involve physicists modeling ice flow, chemists analyzing ice core samples, biologists studying glacier ecosystems, geologists examining glacial landforms, and climatologists interpreting climate records. This collaboration enriches the science, bringing diverse perspectives and expertise. Fieldwork often involves teams living and working together in remote locations, fostering camaraderie and shared purpose. The questions being asked are too complex for any single discipline. Understanding glaciers requires synthesis across fields. This collaborative approach reflects the complexity of Earth's systems and the recognition that solving problems like climate change requires bringing together knowledge from many areas. Glaciers, as subjects of study, unify scientists in common pursuit of understanding. Glaciers, as climate archives, ice cores, reveal past atmospheric carbon dioxide levels. One of the most important discoveries from ice cores is the direct measurement of past atmospheric CO2 concentrations. Air bubbles trapped in the ice contain samples of ancient atmosphere. By analyzing these bubbles, scientists have reconstructed CO2 levels going back 800,000 years. The data show that CO2 has varied naturally, rising and falling in rhythm with ice ages and warm periods. But the current level, over 420 parts per million, is higher than at any point in that entire record. The ice core data provide undeniable evidence that recent increases in CO2 are unprecedented in recent geological history, and that they coincide with industrialization and fossil fuel use. This evidence has been fundamental in establishing the scientific consensus on human-caused climate change. The ancient air trapped in ice speaks clearly, telling us that what is happening now is outside the range of natural variability. Isotopes in ice indicate past temperatures. Water molecules contain different isotopes of oxygen and hydrogen. The ratio of these isotopes in glacier ice depends on the temperature at which the snow fell. Warmer conditions favor heavier isotopes, while colder conditions favor lighter ones. By measuring isotope ratios in ice core layers, scientists can estimate past temperatures with remarkable precision. This technique has allowed researchers to reconstruct temperature changes over hundreds of thousands of years, revealing ice ages, abrupt warming events, and stable warm periods. The isotope record shows that Earth's climate has been highly variable, but also that the rate of current warming is exceptional. Isotope analysis is a powerful tool, turning the chemical composition of ice into a thermometer for the past. It is one of the ways glaciers serve as archives, preserving detailed records of conditions that existed long before humans had instruments to measure them. Volcanic eruptions are recorded as ash layers in glacial ice. When volcanoes erupt explosively, they eject vast quantities of ash into the atmosphere. This ash can travel thousands of kilometers, eventually settling on glaciers and being buried by subsequent snowfall. Years or centuries later, scientists drilling ice cores find these ash layers, thin bands of dark material distinct from the surrounding ice. By analyzing the chemical composition of the ash, researchers can match it to specific eruptions, creating time markers that help date the ice. Some layers correspond to known historical eruptions, like Mount Vesuvius in 79 AD or Krakatoa in 1883. Others are from prehistoric eruptions, long forgotten but preserved in ice. These volcanic markers are invaluable for establishing chronologies and correlating ice cores from different locations. They also provide insights into the frequency and impact of volcanic activity over time. The ash is a geological signature written in ice. Pollen grains in ice reveal ancient vegetation patterns. In addition to dust and ash, Glacier ice traps pollen grains carried by wind from surrounding landscapes. These microscopic grains are remarkably durable and identifiable to specific plant species. By analyzing pollen in ice cores, scientists can reconstruct what plants were growing in the region at different times. An abundance of pine pollen might indicate forests at higher elevations during a warm period, while grass pollen might suggest cooler, more open landscapes. This information complements temperature records from isotopes, providing a fuller picture of past climates and ecosystems. Pollen analysis in ice cores is painstaking work, requiring careful extraction and microscopic identification, but it yields rich insights into how life responded to climate changes. It shows that ice is not just a physical record, but also a biological one, capturing the fingerprints of vanished forests and grasslands. Microbes frozen in ice may hold clues to ancient life. Deep within glaciers, scientists have discovered microorganisms that have been frozen for thousands or even millions of years. Some of these microbes are dormant, in a state of suspended animation. Others appear to be active, living in thin films of liquid water that exist even in extremely cold ice. These discoveries challenge assumptions about the limits of life, showing that organisms can survive in frozen environments for extraordinary lengths of time. They also have implications for astrobiology. If life can persist in Earth's ice, perhaps it could also exist in the ice of Mars, Europa, or other cold worlds. Studying ancient microbes from glaciers helps scientists understand how life adapts to extreme conditions and how ecosystems might function in frozen environments. The ice, in preserving these organisms, offers a window into biology's extremes. The beauty of glaciers. Glaciers glow with an ethereal blue light in certain conditions. There are few sights more beautiful than the deep blue of ancient glacier ice. In ice caves, crevasses, and where old ice is exposed, the color can be so intense it seems otherworldly. This blue is not a trick of the eye or a reflection, but an intrinsic property of the ice itself. Light entering the dense ice is absorbed and scattered, with blue wavelengths penetrating deepest and reflecting back. The effect is most striking when the ice is thick and pure, free of bubbles and impurities. Sunlight filtering through ice caves creates an environment bathed in blue, as if underwater in a frozen sea. Photographers seek out these places, capturing images that convey the serene, cold beauty of glaciers. The blue light feels ancient and pure, a color born from pressure and time, from snow transformed into crystal over centuries. Sunlight refracting through ice crystals creates stunning halos and rainbows. In cold environments where ice crystals are suspended in the air, sunlight can interact with them to create optical phenomena. Sundogs, bright spots flanking the sun, appear when light refracts through hexagonal ice crystals. Halos, rings of light around the sun or moon, form under similar conditions. Occasionally, entire circles or arcs of rainbow-colored light appear in the sky, bending and shifting as the crystals drift. These displays are common near glaciers and in polar regions, adding a touch of magic to already extraordinary landscapes. Indigenous peoples wove these phenomena into stories and used them to predict weather. Today, they continue to inspire awe, reminders of the interplay between light and ice, physics made visible in fleeting, beautiful patterns across the sky. Seracs are towering ice formations sculpted by crevasses. Where glaciers are heavily fractured by intersecting crevasses, blocks of ice are isolated, forming tall, jagged towers called seracs. These formations can be tens of meters high, leaning at precarious angles, their surfaces sharp and glittering. Seracs are beautiful but dangerous. They are unstable, and can collapse without warning. Mountaineers navigating icefalls must move quickly through zones of seracs, aware of the risk. The formations are ever-changing. As the glacier moves and the ice shifts, old seracs collapse and new ones form. Their shapes are sculpted by the same forces that move the glacier, and they stand as temporary monuments to ice in tension. In sunlight, seracs catch the light, casting complex shadows and creating a labyrinth of ice architecture, chaotic yet mesmerizing. Glacial caves are sculpted by flowing meltwater within the ice. In summer, meltwater streams sometimes carve tunnels through or beneath glaciers, creating ice caves. These caves are ephemeral, lasting only as long as conditions allow. Inside, the walls are smooth and sculpted, shaped by flowing water. The ice glows blue, and the sound of dripping water echoes. Light filters through the ice, creating gradients of color. Exploring these caves is both thrilling and dangerous. They can collapse or flood without warning. Yet they offer a glimpse into the glacier's hidden interior, a perspective few get to experience. The caves are artworks of nature, carved by water and ice, existing briefly before the glacier's movement and melting erase them. They are transient wonders, reminding us that even in solid ice, there is flow and change. Alpenglow paints glaciers pink and gold at sunrise and sunset. At dawn and dusk, when the sun is low on the horizon, its light passes through more atmosphere, scattering shorter wavelengths and allowing reds, oranges, and pinks to dominate. When this light strikes glaciers and snow-covered peaks, they glow with warm colors, a phenomenon called alpenglow. The white ice becomes pink, gold, or even crimson, contrasting beautifully with the deepening blue of the sky. The effect lasts only minutes, a fleeting moment of beauty at the transition between day and night. Mountaineers and photographers prize these moments, waking early or staying late to witness the transformation. Alpenglow is a reminder of the subtleties of light, how angle and atmosphere can paint the world in unexpected hues. It is one of nature's gentlest displays, a soft glow on hard ice. Glaciers create landscapes of sublime scale and beauty. Stand before a glacier is to confront nature at its grandest. The sheer scale of these ice masses, the way they dominate valleys and mountains, the sense of age and power they convey, all combine to create a sense of the sublime. This is beauty mixed with awe, a recognition of forces far greater than oneself. Early explorers and romantic artists sought out glaciers for precisely this feeling, the encounter with nature's majesty that humbles and inspires. Modern visitors experience the same emotions, whether viewing from a distance or standing on the ice itself. Glaciers are not just features of geography, they are experiences, moments that stay with those who witness them. In their presence, the distractions of daily life fall away, replaced by wonder at the natural world's grandeur and intricacy. Glaciers in the past. During the last ice age, ice covered a third of Earth's land surface. 20,000 years ago, at the peak of the last glacial maximum, ice sheets extended far beyond their current limits. In North America, ice reached as far south as what is now New York City, and covered all of Canada and much of the northern United States. In Europe, ice blanketed Scandinavia, the British Isles, and parts of Germany and Poland. Similar ice sheets existed in Siberia and Patagonia. Altogether, ice covered about 30% of Earth's land, compared to about 10% today. Sea levels were 120 meters lower because so much water was locked in ice, exposing continental shelves and land bridges. The climate was much colder, and the Earth looked very different. Then, around 18,000 years ago, temperatures began to rise, and the ice started to retreat. By 10,000 years ago, the ice had withdrawn to roughly its present extent, marking the beginning of the Holocene epoch, the current warm period in which human civilization has developed. Glaciers have advanced and retreated many times over millions of years. The Ice Age, 20,000 years ago, was not unique. Earth has experienced many glacial, interglacial cycles over the past 2.6 million years, the Quaternary period. These cycles are driven primarily by variations in Earth's orbit around the Sun, known as Milankovitch cycles, which affect the amount and distribution of solar energy reaching the planet. When conditions favor cooling, ice sheets grow and glaciers advance. When warming occurs, ice retreats. Each cycle lasts roughly 100,000 years, with long cold periods punctuated by shorter warm interglacials. We are currently in an interglacial, a warm period between ice ages. The cycles are recorded in ice cores, ocean sediments, and glacial landforms. Understanding these cycles helps scientists place current climate change in context, showing that while climate has always varied, the current warming is rapid and driven by human activity, not natural orbital changes. Glacial periods shaped the evolution and migration of species. The repeated advance and retreat of glaciers profoundly influenced the evolution and distribution of life on Earth. During glacial periods, many species were forced to migrate to warmer regions or adapt to colder conditions. Some, like woolly mammoths and saber-toothed cats, thrived in the cold and disappeared when the climate warmed. Others survived in refugia, small pockets of suitable habitat, and recolonized broader areas when ice retreated. The movement of ice also created barriers, isolating populations and leading to the evolution of new species. Glaciation influenced human evolution as well. Early humans had to adapt to changing climates, migrating out of Africa and into Europe and Asia as conditions allowed. The landscapes we see today, the distribution of forests, grasslands, and deserts, are partly legacies of these Ice Age cycles. Glaciers have been shapers not just of land, but of life itself. Megafloods from glacial lake bursts carved dramatic landscapes. During the retreat of ice sheets, massive glacial lakes formed, dammed by ice or moraine. When these dams failed, the results were catastrophic. One of the most famous examples is the Missoula floods in North America. As the ice sheet retreated, glacial Lake Missoula formed in what is now Montana, containing more water than Lakes Erie and Ontario combined. Repeatedly, the ice dam failed, and the lake drained in a matter of days, sending torrents of water racing across Washington state. These megafloods carved the channeled scablands, a landscape of deep gorges, dry waterfalls, and giant ripple marks. The floods deposited massive boulders and reshaped the Columbia River Valley. Similar megafloods occurred elsewhere as ice sheets retreated. These events were among the most powerful floods in Earth's history, demonstrating the immense power of water released from melting ice. They are reminders of the dynamic and sometimes violent nature of glacial landscapes in transition. Glaciers preserved ancient humans and artifacts in frozen tombs. In a few remarkable cases, glaciers have preserved human bodies and belongings for thousands of years. The most famous is Ötzi, the Iceman. Discovered in 1,991 inches, the Alps on the border between Austria and Italy. Ötzi lived around 3,300 BCE and was naturally mummified by the cold, dry conditions of the glacier that covered him shortly after his death. His body, clothing, tools, and even his last meal were preserved, providing an extraordinary snapshot of life in the Copper Age. Other discoveries include ancient hunters in ice patches in North America, complete with bows, arrows, and clothing. These finds are scientifically invaluable, offering direct evidence of past cultures and technologies. They also underscore the power of ice to preserve, acting as a time capsule that protects organic material from decay. As glaciers melt due to warming, more such discoveries are emerging, though the race is on to document and preserve them before they deteriorate. The slow work of ice glaciers moves so slowly their motion is often imperceptible. One of the defining characteristics of glaciers is their slowness. While they flow, the movement is so gradual that watching a glacier, you would see no motion at all. It takes specialized instruments, time-lapse photography, or careful measurements over weeks and months to detect the flow. Some glaciers move only a few centimeters per day. Others, particularly in warmer regions or during surges, can move meters per day, but even that is slow compared to rivers or wind. This slowness is deceptive. Over years and decades, glaciers travel kilometers, carving valleys and reshaping mountains. The ice that emerges at a glacier's terminus may have started its journey centuries ago, high in the accumulation zone. This patient movement is one of the glacier's most profound characteristics, a reminder that not all change is fast, that slow forces can be immensely powerful. Over millennia, glaciers can carve deep fjords and valleys. The erosive power of glaciers, applied patiently over thousands or millions of years, creates some of Earth's most dramatic landforms. Fjords, those deep, steep-walled inlets, were carved by glaciers during the ice ages. The ice, thick and heavy, scoured the valleys to depths far below sea level, plucking rock from the walls and grinding the bedrock smooth. When the ice melted and sea levels rose, the ocean flooded these valleys, creating fjords. Similarly, the U-shaped valleys of mountain ranges were carved by glaciers, their flat floors and straight walls the signature of ice at work. This erosion is slow, measured in millimeters per year, but over geologic time, it reshapes entire landscapes. The valleys we hike through, the fjords we admire, are the legacy of ice's patient, persistent labor, grinding stone with the weight of centuries. The longest glaciers can stretch over 100 kilometers, while many glaciers are small, confined to mountain cirques or short valleys. Some are immense. The Lambert Glacier in Antarctica is the world's longest, stretching over 400 kilometers from its origin to the sea. In Greenland and elsewhere, outlet glaciers that drain ice sheets can be tens or hundreds of kilometers long. These rivers of ice flow through vast landscapes, their surfaces marked by crevasses, moraines, and meltwater streams. Their scale is difficult to grasp without seeing them from above or traveling along them for hours or days. These long glaciers are highways of ice, transporting frozen water from interiors to coasts, from high elevations to sea level, over distances that dwarf human structures. They are monuments to the persistence of cold, enduring features in landscapes shaped by time. Ice can remember stresses and strains from decades past. Glacier ice has a kind of memory. When ice is deformed by stress, the crystal structure changes, aligning in certain directions. This alignment persists even after the stress is removed, creating a record within the ice. Scientists studying ice can detect these deformations and infer past stresses, learning about changes in glacier flow or thickness that occurred decades or even centuries ago. This is called ice fabric analysis, and it provides insights into glacier history that would otherwise be lost. The ice, in a sense, remembers being squeezed, stretched, or bent, and that memory is readable by those with the knowledge to interpret it. It is one of many ways glaciers serve as archives, storing information not just in layers but in the very structure of the ice itself. Every grain of ice in a glacier has a unique history. A glacier is not a uniform mass, but a collection of countless ice crystals, each with its own origin. Some grains come from snow that fell centuries ago, others from just a few years past. As the ice flows and deforms, grains change shape, recrystallize, and interact with neighbors. Deep within the glacier, under high pressure and temperature, grains can grow large, while near the surface, they remain small. Each grain has experienced a unique journey through the glacier, subjected to different stresses and conditions. This microscopic diversity is invisible from the outside, but it affects how the ice behaves. Scientists studying glacier mechanics analyze ice grains under microscopes, learning how their properties influence flow. This attention to the smallest components reveals that glaciers, like all natural systems, are complex aggregations of individual elements, each contributing to the whole. Reflections on ice glaciers connect us to deep time and planetary processes. To contemplate a glacier is to think in geologic time. The ice beneath your feet may be older than recorded history. The valley it carved was shaped over tens of thousands of years. The climate cycles recorded in its layers span hundreds of millennia. Glaciers link the human scale of days and years to the planetary scale of epochs and eras. They remind us that Earth is ancient, dynamic, and shaped by processes far larger and slower than our individual lives. This perspective is humbling but also inspiring. It places human existence in context, showing us as part of a much longer story. Glaciers teach patience, the power of gradual change, and the interconnectedness of Earth's systems. They invite us to think beyond ourselves, to consider the deep past and the distant future, and to recognize our role in the ongoing story of the planet. Ice holds a mirror to our changing world. Glaciers do not advocate or opine, they simply respond to physical conditions. Yet in their retreat, they hold up a mirror, reflecting back the consequences of human activity. The warming that causes glaciers to melt is driven by greenhouse gases emitted from burning fossil fuels, deforestation, and industrial processes. The evidence is clear in the shrinking ice, the rising meltwater rivers, the disappearing landscapes. Glaciers are witnesses to change, impartial and honest. They show us what is happening, not through words, but through their own transformation. This makes them powerful symbols in climate discourse, tangible evidence that is difficult to deny. They ask us to consider what kind of world we are creating and what legacy we will leave. The reflection they offer is not always comfortable, but it is necessary. Glaciers inspire wonder and contemplation. There is something about glaciers that invites stillness and reflection. Perhaps it is their scale, their age, or their beauty. Perhaps it is the way they embody contradictions, solid yet flowing, ancient yet changing, harsh yet beautiful. Standing before a glacier, many people feel a sense of peace, a quieting of the mind's chatter. The ice does not demand anything of us, it simply is. This quality makes glaciers places of contemplation, where people come not just to see but to think and feel. They inspire poetry, art, and philosophy. They remind us of the sublime, that mixture of beauty and awe that transcends everyday experience. In a world that often feels hurried and fragmented, glaciers offer a different pace, a connection to something vast and enduring. The fate of glaciers is intertwined with humanity's future. What happens to glaciers in the coming decades and centuries will depend largely on human choices. If greenhouse gas emissions continue unabated, most mountain glaciers will disappear, and ice sheets will lose substantial mass, raising sea levels and altering water supplies for billions of people. If, however, humanity succeeds in reducing emissions and limiting warming, some glaciers may stabilize, and the pace of change will slow. The future is not predetermined. It is being written now, in the decisions made by individuals, communities, and nations. Glaciers are thus not just subjects of scientific study, but stakes in a global challenge. Their preservation, or lack thereof, will reflect the values and priorities of this era. They are part of our collective inheritance, and what we do with them will be remembered. Closing thoughts. Glaciers are both ordinary ice and extraordinary phenomena. At their simplest, glaciers are just frozen water, the same substance that forms in your freezer or falls as snow. Yet they are also extraordinary, ancient, massive, dynamic, and beautiful. This duality is part of their fascination. They are made of something familiar, yet they do things and exist on scales that are anything but. A glacier is both simple and complex, mundane and sublime. It is ice, and yet it is so much more. A force that shapes landscapes, stores history, influences climate, and inspires awe. To understand glaciers is to appreciate how the ordinary can become extraordinary when given time, scale, and the right conditions. They remind us that the world is full of wonders, some obvious and some hidden in plain sight. Every glacier is unique, shaped by its particular environment. No two glaciers are exactly alike. Each is shaped by the specific conditions of its location, the climate, the topography, the snowfall patterns, the bedrock beneath. One glacier might be steep and fractured, another smooth and gently sloping. One might advance, another retreat. Some are pristine white, others dark with debris. This diversity makes glaciology endlessly interesting. Each glacier is a case study, offering insights that may or may not apply elsewhere. It also means that experiencing glaciers requires visiting them, seeing them in their particular contexts. Photographs and descriptions can convey much, but standing before a glacier, hearing its sounds, feeling its cold breath, that is irreplaceable. Each glacier has its own character, its own story written in ice. In their silence, glaciers speak volumes. Glaciers do not shout or clamor for attention. They exist quietly, moving slowly, changing at their own pace. Yet they communicate powerfully. Through their advance and retreat, they tell stories of climate. Through their layers, they record history. Through their presence, they shape ecosystems and cultures. Scientists listen to this silent language, interpreting measurements and observations, but others listen too, in different ways. Artists see beauty. Philosophers find metaphors. Communities recognize kinship. The silence of glaciers is not empty. It is full of meaning, waiting for those who take the time to listen. In a noisy world, their quietness is a gift, an invitation to slow down, to pay attention, to understand. Glaciers teach patience and the power of slow change. In an age of instant gratification and rapid transformation, glaciers remind us of a different mode of being. They change slowly, almost imperceptibly, yet over time they accomplish feats of immense power. They carve mountains, shape continents, and influence oceans. Their lesson is clear. Patience and persistence are powerful. Not everything worth doing happens quickly. Some things require time, steady effort applied over long periods. This applies not just to geology, but to life, to relationships, to the work of building a better world. Glaciers teach that slow does not mean weak, that gradual does not mean insignificant. In their patient flow, there is wisdom worth heeding. The ice holds memories of times we will never see. Within glaciers lie frozen fragments of atmospheres long vanished, pollen from forests now gone, dust from eruptions witnessed by no living person. These memories are preserved with fidelity, waiting to be discovered and interpreted. In a very real sense, glaciers remember for us, holding the past in cold storage. This makes them precious beyond measure. When a glacier melts, those memories are lost forever, the archive destroyed. This is one of the sadder aspects of glacier retreat. It is not just ice that disappears, but also history, irreplaceable records of Earth's past. Protecting glaciers means protecting these memories, ensuring that future generations can learn from them. The ice holds what we have forgotten or never knew, and in its depths, there is knowledge waiting to be found. As you rest here, let the calm of glaciers carry you. Imagine yourself lying on soft grass beside a glacier, the air cool and fresh. You can hear the distant trickle of meltwater, the occasional crack of ice settling. The glacier stretches before you, blue-white and ancient, a presence both solid and somehow timeless. There is nothing you need to do, nowhere you need to be. The ice has been here for thousands of years, and it will be here tomorrow. Time moves differently here, measured not in hours but in seasons and centuries. You breathe deeply, and with each breath, you feel more relaxed, more at peace. The glacier's stillness flows into you, quieting your mind, easing your body. You are safe here, held by the earth, cooled by the ice, surrounded by beauty. Let yourself drift, like a snowflake settling on the glacier's surface, finding your place, becoming part of the quiet. Let the ice carry you into rest, into dreams as deep and blue as the glacial depths. Close your eyes, breathe, sleep. And so, dear listener, our journey through the world of glaciers comes to a close. We have wandered across ice sheets and valley glaciers, explored caves glowing blue, and traced the history written in ancient ice. We have learned how glaciers form and move, how they shape landscapes and influence climate, how they hold memories and inspire wonder. These frozen rivers are both timeless and changing, witnesses to Earth's past and indicators of its future. They remind us of the power of nature, the interconnectedness of Earth's systems, and the importance of paying attention to the world around us. As you lie here, letting your breath fall into an easy rhythm, picture the vast ice fields under starlit skies, the quiet flow of frozen water down mountain valleys, the blue depths that hold centuries of snow. See the meltwater streams, the moraines, the landscapes shaped by patient erosion. All of it is still there, continuing its ancient work, whether we watch or not. The glaciers flow on, carrying time within them, slowly transforming snow into stone, shaping the world one grain of ice at a time. If you are still awake, you may continue on to the next video when you are ready. But if your eyes have grown heavy, if the weight of rest has settled over you, then let go. Let the stillness of ice hold you, the cold beauty of glaciers surround you, and drift into the deep, quiet sleep that comes when mind and body finally release. Good night.